In this section, I'll talk about pulses as compared to periodic waves, basic reflection, the displacement of a point on a transverse wave, and basic interference. So let's start by talking about the difference between a pulse and a periodic wave. If you take a piece of string and tie it to a fence, you can flick it up once and create a pulse. A pulse on a diagram will look like this. That or that is considered a single pulse. Now, when we repeat that pulse up and down, we create a periodic wave. Now, you have to flick it up and down with a specific period or a specific frequency so that it's symmetric, top and bottom, and so that the period stays constant. This would be a periodic wave. Up, down, up, down, up, down. I'm trying to draw it as symmetrically as I can. This is a periodic wave. This or this is considered a single pulse. Now let's talk about basic reflection. When you tie a piece of string to a rigid object, like a wall, and you send a pulse down the string, that pulse will reflect off of the rigid wall. When it reflects off of the rigid wall, it comes back inverted compared to the original direction. Again, you're sending it toward a rigid wall, a material that is more dense and unable to move. When it returns, right, it's going this way. This is the original velocity, and it's up on top. It stays on top all the way across, hits the rigid wall, reflects off the wall, and now its velocity is back in the opposite direction, and it's also on the bottom, and it stays on the bottom the whole time that it's coming back. Right? So when a pulse hits a rigid wall, it reflects back and inverts. Now, what happens when a pulse like that hits a medium that is less dense and more flexible? Let's try that. If we have a very thick piece of string and we send a pulse down that very thick piece of, let's call it rope, and we attach that very thick piece of rope to a much thinner piece of rope, and we attach this at the opposite end. Well, I'm sending this pulse down this thick piece of rope, and what will happen is that the pulse will go down. All right, I shouldn't have drawn him there. The pulse will go down and be transmitted to the thinner piece of rope. It will travel faster in the thinner piece of rope, and it will also reflect back. When it hits this interface between the two ropes, it will be reflected back. But since this second material is less dense and much more flexible, when it reflects back, it will stay on top. So it will be transmitted from this piece of rope to this piece of rope, and part of it will keep going that way, and part of it will reflect back, but it will stay on top. It will not be inverted because this material is not rigid compared to this material. And again, because these are two different media, right, the medium, two different media, the speed of the pulse in this rope and this rope will be different. All right? So, just to sum up, when a pulse reflects off a rigid object, it inverts. When a pulse reflects off a less rigid object, it stays at the same side, up and back on the upside. All right, so that was a basic reflection. Now let's talk about how a point on a transverse wave moves when the wave passes through it. Here we have a single wave pulse on a string, and here is a point. Let's call this point A. And we'd like to know, how is point A going to move when this pulse passes through it? So let's see. Well, this wave is going to travel. Now, I have to tell you what direction it's traveling in. It's traveling this way, to the right. Now, when this wave gets to here, now keep in mind this is a transverse wave, so A only has two options. A can go up or A can go down. Since the wave is traveling in this direction, and a transverse wave must vibrate perpendicular to the direction that the wave is traveling. Let me show you perpendicular. The wave is traveling in this direction, to the east or to the right, and it's vibrating perpendicular, up and down. Now the wave could also be traveling to the left, and it would still be vibrating up and down. But this particular wave, we've said, is traveling to the right. Now, when this pulse gets to point A, I'm going to draw a picture of this pulse just getting to point A, right here. All right, so you see that when this pulse gets to point A, that point A will be down here. So how did point A move? It moved down first. All right, now, the pulse continues to move to the right. So let's see what happens when the pulse moves a little further to the right. When the pulse moves a little further to the right, right now it's there. Point A is now up here. Point A moved from down here to up here. So keep in mind, point A went down and then up. All right, but again, that would be straight down and straight up. All right, and then, of course, as this part of the pulse gets to point A comes back down again. So how does point A move as the pulse passes it? For this particular pulse, as it passes point A is going to have to go down, that's straight down, and then up, that's straight up, down to the equilibrium position. So in essence, after the pulse passes by point A, the displacement of point A ultimately is 0. Point A goes down a little, All right, down 1, up 1, 2, and then down 1. So ultimately, the displacement of point A is 0, and the wave passes by. Here's the wave over here, passing right by point A. It's going that way. All right? Now, I want to show you a little trick that works for questions like this, where you're being asked, which way will the point go first? All right, so let's try an example like this. And we'll call this one point X. And we'd like to know, as this wave, as this pulse, traveling in this direction, passes by point X, how does point X move? All you need to really do is take your finger and just work backwards. If the wave is going in that direction, then you just move your finger backwards. So point X will go first up, then down, then up again. So that would be vertically up, in other words, straight up. X would go straight up as the wave gets to it, vertically up, then vertically down, straight down, and then vertically up. And again, once the wave is passed, point X is right back where it started from. Its displacement is 0. All right? We could try one more question like that. I'll make an entire periodic wave, a couple of wave cycles, 1, 2, 3. There's 3 wave cycles. And I'll put point C here, point D here, and point E there. All right, so now let's say that this wave is traveling to the right. Okay? How will point C move if this wave is traveling to the right? Point C will go down, then up, then down, etc. Now remember, point C will go straight down, then straight up. Because point C is not moving horizontally. Point C, this is a transverse wave. Point C moves straight up and straight down, perpendicular to the direction of motion. So C is going to go down and then up, etc., depending on how many more waves are coming. Now what about point D? What is point D going to do first? Well, point D has to get up to here because this is the part, the crest is coming to point D next. So point D is going to have to go straight up first and then down, etc. What about point E? Well, here's the trough. The trough will be at point E next. So point E is going to have to go down and then up. Down and then up and then down again, etc., etc. All right, so you simply move your finger to the left to see how the point will move next. Now, just one other little point here. What if the wave was traveling to the left? Which is obviously quite possible. So here's another wave. All right, and here's, we'll put point A here, we'll put point B here, and we'll put point C here. And we'll say that this wave is traveling to the left. That's a negative velocity. This wave is traveling to the left. Well, going by the handy little rule that I told you, if the wave is traveling that way, simply move your finger backwards to see how the point moves. A will go straight down and then straight up. So A will move like this, straight down and then straight up. And of course, as the wave keeps going, that's what A is going to do. Down and up and down and up and down and up. All right, A will go straight down and straight up. How is B going to move if the wave is moving to the left? First he's going to have to go up, and then he's going to go down. How is C going to move? C is at the crest, so C will move down and then up. All right? Now, again, on a transverse wave, the wave particles move straight up and straight down, or rather perpendicular to the direction of motion. If the wave is traveling east or west, the particles are going to vibrate up and down, north and south. Now, what about a longitudinal wave? For a longitudinal wave, compression, rarefaction, compression, rarefaction, compression, rarefaction. All right, this particle will move to the right and to the left. The wave is traveling, let's say, for example, to the right. The particle will vibrate left and right, just like that. All right, I don't know which one is going to happen first, but it's vibrating to the left and to the right. Again, these particles are vibrating parallel to the direction of motion because this is a longitudinal wave. A sound wave would be a good example of a longitudinal wave. Now, the last thing that I'd like to talk about in this section is basic interference. You have constructive interference, and constructive interference would occur when crest meets crest or when trough meets trough. That would be crest meets crest or trough meets trough. Again, this is constructive interference. For example, let's take a pulse traveling in this direction with this height and a smaller pulse traveling in the opposite direction with that height. Now, I would say this guy is about +2 and this guy is about +1. +1, right, and +2. Now, they're going to meet here somewhere. And when they meet, when two pulses or two waves are in the same place at the same time, they interfere with each other. If they're both crests or both troughs, that interference will be constructive. In other words, they'll work together and their amplitude will increase. So let's see what these two look like when they come together. Now, what I'd like to do is show you several progressions of how these guys will move and what will happen to them. So if I have a +2 and a +1, and he's traveling this way and he's traveling that way, when they come together in the center, they will total +3. Right, so this is +1, that's about +2, so this guy is about +3. Now, they interfere with each other here when they're together, but +1 continues to travel that way, and +2 continues to travel that way. So basically, they pass right through each other and come out undisturbed. So here's +2 continuing that way, and there's +1 continuing that way. So here they're coming at each other, here they interfere with each other, and here they have passed through each other undisturbed. One more example of constructive interference. What if we had a kind of a square, and a kind of a hump, and they're coming toward each other. He's going that way, he's going that way. When they're together, you'll have the square and the hump. Something like that. Then they pass through each other undisturbed. So, the hump will be on this side, the square will be on that side. And he keeps going that way, and he keeps going that way. All right? So again, all of these are examples of constructive interference. You can also have two troughs. Two troughs interfering with each other will also be constructive. So for example, a trough and a trough. He's going this way, he's going this way. When they come together, if this is -1 and -1, they're on the bottom, then together they would be -2, and then they pass through each other undisturbed. -1 and -1, he's going that way, he's going that way. Okay? So when crest meets crest, or trough meets trough, you have constructive interference. Now, what about destructive interference? Let's take a look at a few examples of destructive interference. Now, I will talk about constructive and destructive interference at more length in the section on diffraction and interference. Remember, this is a basic look at constructive and destructive interference. Here comes your destructive interference. Basically, destructive interference occurs when crest meets trough. So in other words, when a positive and a negative come together, to some extent or completely, they will cancel each other out. So let's try first a +2 coming together with a -1. All right, so here's a +2 and here's a -1. When they come together, it will be +1. Then they will pass through each other undisturbed, and you'll have the -1 on this side and the +2 on that side. He's going that way, he's going that way. Sorry, forgot to label these guys. He was originally going that way, and he was going that way. So this is destructive interference, a crest meeting a trough, and it is partially canceled. Partially canceled. Now, what if you had a +2 meeting a -2? If a +2 going that way meets a -2 going that way, what's the amplitude? Briefly, until he continues that way. So he's going that way, he's going that way. Again, they interfere with each other, and then they pass each other relatively undisturbed. All right, so this was several examples of destructive interference.